Hello everybody, this is Avantik here. Today we'll be discussing about cluster analysis. The agenda for today's discussion is as follows. We'll first understand what is unsupervised learning, what is clustering. For clustering uses this similarity and distance calculation a lot. There are a few techniques with which we'll try to go through. Followed by that, we'll be understanding what is the optimization function in clustering, types of clustering methods, which includes your partitioning clustering, hierarchical clustering, and density-based clustering. Will get to understand k-means, mean shift, agolometric, db scan, and then we'll try to see how to measure the clustering technique for the particular data. Right. So this is all that we'll discuss. Let's start with introduction to unsupervised learning. Unsupervised learning is a type of machine learning where you try where your target is not available. You have the data, you don't have the target, and you try to find relationship between the data. Okay, to put it in API way, in supervised learning, in fit function, you pass x and y. In the unsupervised learning, you'll not pass y over there, just x, and you'll try to your unsupervised learning methods will try to find relationship between the data. It is mostly used to explore data. For example, you have your customer records. You want to find out what is the which are the similar type of customers. Okay, so let's now get into clustering. This is one of the unsupervised learning method. Apart from clustering, you have associations, which we'll see in the later part of the course. Clustering. Let's understand what is clustering. Okay, so a learning technique which tries to group data in such a way that data belonging to same group or cluster shows similar properties, and data belonging to different cluster will show little different properties. So that's what clustering is. Using different methods, you will basically try to group data. Applications of clusterings are huge. It is extensively used in data mining related activities. Okay, and if what it does, it allows you to automatically organize the data. Okay, for example, you want to do some machine learning on the data and you don't have any label. So if you want to label the data, you can use clustering techniques to see if you can, if your clustering methods can group similar data together on which you can do your labeling activity. It also helps us in understanding the underlying, structure of the data. As I explained earlier, it can be used for customer segmentation. Let's take an example of Vodafone. Okay, so they have huge customer base. Now they want to group customers so that they can have some advertising technique for them. Okay, so if in a group of customer they find, okay, these are the people who spend less, you can have a different marketing strategy for them. They can segregate customers into and they realize that these are the high-end customers. They have a altogether different marketing strategy for them. Then you have all the user base. You want to recommend social groups for them, right? This is what another approach for that. So let me try to plot some data from Matplotlib, and we are using, as you can see, make blobs here. So that and this is how we are using number of features 2, number of samples 1000, number of centers 3. Okay, and cluster standard deviation is 1, random state is 3, so that every time you're able to reproduce theme distribution. So you can see what you're doing here is generating 3 clusters. Okay, so this is like natural 2 dimensions, but it's easy to understand. This is one cluster, this is another cluster, this is another cluster, but it might not be this easy when the dimension increases. Okay, so let's see the next topic, which is about finding similarity or difference between data. Okay, let's understand distance or similarity function. Okay, so now as the clustering defines, you are trying to find out data belonging to same cluster. Okay, so that is the similarity. So you have to figure out the data which is similar to a particular data. That is what is similarity function. Okay, and if you want to find out, so you want to reduce the distance between the 2 data. That is where your distance functions comes into picture. Okay, so let's see now. Okay, that's a fundamental thing that we'll do with clustering. We want to figure out data in the same cluster so that they are similar, right? And data which belongs to different cluster, they will be a little different. So there are 3 methods of such distance calculation. So remember, you're talking about data which is a much higher dimension. So the generic method is Minkowski breed of calculation, and this is how it's calculated. It's very simple. Okay, so say x and y are your 2 points, right? 2 data. And of course, the dimensions of x and y can be, you can imagine them as n dimension. Okay, and p is a probabilistic factor. Okay, so what you're doing here, for each column xi y, I is a column number. For each column, you're finding the difference between x and y, and you are squaring it up. In case of Euclidean, that becomes Euclidean distance, and your p is equal to 1 in case of Manhattan distance. So this is what it is. For example, in case of Euclidean, which is the generally used distance vector for most of the algorithms, what you're doing here, you're calculating the difference between both the points. You're doing a mod of them and square of them, and sum of all those points, then square root of them, right? This is your Euclidean distance. So that's what is your Manhattan and Euclidean distance, right? Okay, and Minkowski is the superset of it. If p is equal to 1, it's Manhattan. If p is equal to 2, it's Euclidean. Okay. Other technique is cosine distance. So cosine distance is very much suited for data. If you want to find text which are similar to each other, vectorize them and then find cosine distances between them. That will tell you how similar they are. Okay, and it's basically a dot p. That's the dot product of these, and you're dividing it by mod of a and mod of b. That's basically typically sum of square of all the a values and a square root of them, sum of square of b values and square root of them. Right? That is cosine similarity. It is very useful in finding which text is similar to that. So these are the three methods of vector distance calculation. So you have all these APIs available in matrices.pairwise. You have Euclidean distance, cosine distance, and Manhattan distance. Pass the two data over here, it will calculate the distances between them. Okay, then you have, this is Euclidean distance for you. If you want to find distance between x and 0, 0, that's what it is finding you, right? And similarly, we can use cosine distance, Manhattan distance. All these are present in your pairwise library, as you can see here. Pairwise. Okay, followed by that, we'll be getting into clustering optimization. Let's now treat and understand clustering as an optimization problem. What you're trying to do using any of the algorithm is you're trying to minimize intra-cluster distance. That means you're trying to make, bring all the points in a cluster whose intra-cluster distance are less, and you're trying to separate out or maximize inter-cluster distance. So between the cluster, you're trying to maximize the distance. In the cluster, you're trying to minimize the distance between the points. That's what clustering is all about. Okay. Now let's understand types of clustering after this. Okay. Now types of clustering. That's what we'll discuss now. There are three major types: partitioning methods, hierarchical methods, density-based methods. Partitioning-based method is about, you say, for example, you have 10 data points. You will divide this 10 data points into k partitions. Okay, the processes initially will randomly create partitions, and then you'll gradually move the points, the participating data from each of the clusters to another, so that you optimize the cluster using, you try to maximize the distance between the clusters, and you try to minimize intra-cluster distances. That's the whole point. Okay, there are two methods we'll try to understand in this technique. One is k-means, other is mean shift. The next technique is hierarchical methods. This methods does hierarchical decomposition of data sets. What it means is, there are two approaches that you take. You fundamentally create one cluster out of all the data points, then try to break down this single cluster into multiple clusters in step by step. So that is where it's hierarchical. Other approach is you start with each data belonging to one cluster, and you try to combine such clusters and create clusters of bigger sizes. Okay, so that's typically where you decide how many clusters you want. You stop your merging there. Okay, so that's what is hierarchical methods. Your cluster building is a hierarchical process. You go from top down or bottom to up. The third method is density based methods. So the above two methods, partitioning and hierarchical, it uses distance vectors, right? So that's why the clusters that is formed by them is it's spherical in nature. Okay, and that's always not the case. Sometimes you have clusters which is not spherical in nature. Okay, so that is where your density based clusters can come into picture. So what it does in this technique, it just data tries to go to the cluster which just forms a bigger cluster, right? So as long as it does not exceed that threshold. So if you have a point, it tries to find a cluster near it, which can be of any shape. Okay, so it's not based on distance vector. So that's why density based clusters can be of any shapes. So let's proceed further with, understanding more on partitioning methods. Partitioning method. Let's understand k-means. Okay, so let's understand this with the visualization. We can, and thanks to the folks who created this. Say we have 100 points here. You can see those white points at 100 points. And what we want to do, we want to create 5 clusters out of these 100 points. So the first step is choosing 5 random centroids. Okay, you can choose this centroid, from the data itself, or you can figure out some numbers within the range. Generally, it is a practice to choose this centroid from the data itself. Okay, so you can see the colored point as the centroids. The first step is from this randomly chosen centroid. For each point, try to find the nearest centroid and connect to it. This is the assignment stage. That's the first thing. From each point, you find the nearest centroid and connect to it. The next step is recalculation of centroid. Centroid recalculation, you can imagine this as, mean of all these points. Okay, so mean of these points will be, one of the like x value of this plus x value of this plus x value of this of all this divided by number of points. Similarly, you do that for y. So that will be centroid calculation. Okay, so now you again calculate the centroid for all these points for all these clusters. So once you calculate the centroid, your centroid reassignment will happen for the cluster. Okay, you can see this happened. It moved towards more stable position. Once the centroid recalculation happens, time to see if there are if there is a requirement of centroid reassignment for each of the point. Like, take an example of, say this point, it might be closer to this than this. So now the reassignment will happen. A point like this, which might be a point like this, which is closer to this than this, right? So this is what your centroid reassignment for the clusters. So that's what happens now. So you can see again some point reassignment happen. The next step to this is, again, we can see a new clusters formed. Recalculate the centroid. That's the next step. So you'll continue this step of recalculation of centroid and reassignment till the clusters are stabilized. That means there is no reassignment. Okay, so if I continue doing this, you can see my clusters have stabilized. Okay, that's the algorithm, and that's the minimization function. This is the centroid coordinates, and this is each point coordinates. This is the thing you're trying to minimize. Okay, and this is the algorithm that we just discussed. Okay, let's now do it in APIs. We are generating blobs data. We can see 3 clusters over here. Make blobs, plotting the data. We want to use k-means, and we are telling here explicitly that we want 3 clusters. That's what is required in k-means. You need to tell how many clusters you're looking for. Then after that, we are training the model. And as we discussed earlier, this is unsupervised learning. So you don't pass y over here, x. Okay, and then followed by that, once the model is trained, k-means.predict will give you the class to which, or the cluster number. So we can see here, that's what we are using as a color. And we can see here that, these 3 belongs to different clusters. Okay, and let's now try to use k-means for different type of data. We are generating make moons. Okay, so that it's not really in the cluster shape. We are generating data in this format. We now want to apply k-means here and see if it's making sense to us. Technically, this can be one cluster, this can be one cluster. Let's see if k-mean is able to solve this problem. So 2 clusters that we know, and when we train the model and then use k-means for that, we can see here it's pitching this as one cluster and this as one cluster. Okay, so that's what k-means. K-means, that's the limitation of k-means. It assumes that clusters are convex and behaves poorly for elongated clusters. Things like this. K-means also tries to find the local minima. So, you might have to experiment with different initial points to get to the best option. Okay. Then followed by this, we'll get into understanding of mean shift. So mean shift also is a, centroid based algorithm. Okay. But it tries to move data to the higher density area. You can imagine this as, if you are in a foggy field. Okay. And all of a sudden there is some alien attack. Okay, where would you move? You'll move to bigger masses, isn't it? That's what the concept of mean shift. Okay, so say we are generating data like this. Okay, and if you use mean shift over here, right? This is the model that we are trying to use, mean shift, and mean shift dot fit, and you're passing all the data over here, and on doing the prediction, right? So this is the mean shift prediction. You can see it forms two clusters. Point to be noted here is, unlike k-means, you don't pass any k here. Okay, so it tries to form as big a cluster as possible. So in this case, we have two clusters. Okay, and if you do the same thing with k-means, and if you mention 4 clusters, we can see here 4 clusters. Okay, so that's the difference between k-means and mean shift. Let's get into the next clustering method, that is hierarchical clustering. A method in which actually you start with either each data belonging to one cluster, then you try to merge clusters which are very similar and create a bigger cluster. This is your bottom up approach. This is what is agglomeric method. The other approach is you start with with the assumption that all the data belongs to one cluster, then create a homogeneous group out of it by splitting it again and again. This is your divisive method. This is a top down approach. So in all this technique, there is a hierarchy involved. Like the entire clustering process involves multiple times creating clusters or splitting clusters out of it. That is why this is known as hierarchical clustering. So first we'll deal with agglomeric method, and that's what we will focus. Okay, so the entire process starts with assigning one data to each cluster. Okay, then finding the similarity between the cluster and combining most similar clusters together. Okay, so combining clusters with higher similarity, that's the step over here. So there are the differences between different sub techniques of agglomeric method is how you find similar cluster. Either you can calculate the farthest point between the clusters, or closest point between the clusters. Okay, so up to you. There are 4 techniques by which you can find similarity between clusters. Okay, let's see it in code. Again, we are generating moons here. Remember how we did for k-means and mean shift for this particular data sets. Let's now see agglomeric method for this. So we have this agglomeric method, and the linkage is single. That means we are making use of the farthest point. Okay, and using that, okay, affinity is Euclidean. That means the vector distance is calculated using Euclidean, and we now see the points, how they are classified. Looks good, right? Okay, so that's what is your agglomeric method doing here. Okay, that's all about. Let's understand density-based clustering, that is dbScan. What it tries to do is it just tries to find a group to which it is closer to, and it becomes part of it. That's how simple it is. Okay, so let's understand with this data. So we are generating data here. You can see it's quite overlapping, of course. So we have this dbScan as part of the cluster. We are scaling the data, and then dbScan takes a parameter EPS. EPS is a measure of how what is the extent to which you can allow a data to be part of a cluster, right? So if you increase the value of EPS, what you're trying to tell here is the distance that you accept a point to be a part of a cluster. Okay, so that's the meaning of it. So once you do this, you can see the data is divided into 3 clusters, and you can see some purple points here. These are the points which didn't belong to any data, any cluster. That's because it is exceeding your EPS value. Okay, so each point try to find which is the closest dense cluster, and it belongs to that. Okay, so that's how it is. Okay, you can use dbScan for outlier detection also. I'll touch this again in outlier detection module. Once you create cluster, of course, you need a way to measure how good clusters are they. So there are 2 major techniques. Okay, one is supervised technique. Supervised technique is you're trying to see if all the data that belongs to one cluster, what is the either the cluster is homogeneous. That means though you didn't use the class information for training the model. So okay, so the next thing is how to measure performance of clusters. So this module, this discussion, we have already covered in your model selection and evaluation phase. So you can refer to that video. okay, or that nodes to understand how do you measure the cluster. So once you have created the cluster, you need to use this technique to understand it. So I have used this technique. So what will we use? We'll find the optimal number of clusters to be used. Say we have a data like this, right? So we want to figure out what is the optimum number of clusters. In this case, we are using k-means, and so that's what we'll k-means, and we are using the Silhouette score, okay? And the Silhouette score will be in the scale of 0 to 1, okay? So closer to 1 is better. So for different values of number of clusters, you're training this model and you're figuring out these values, 0.7, 0.5, 0.6, and you can see here that 2 is the optimal number of clusters. Yeah. So that's all from this video. Okay. Thanks a lot, guys.